Capacitors are a device for storing electric charge and electrical energy. They consist of two conductors called plates, which are separated by an insulator, which is known as a dielectric. The first capacitors looked a bit like jars, and they were known as Leyden jars. Now, each of the plates of the capacitor carries an equal amount of positive and negative charge. And when we discharge the capacitor, negative charge in the form of electrons flows from the negative plate to the positive plate, and the charge is neutralized. The most important properties of a capacitor are its capacitance and its maximum voltage rating. As you add more charge to the capacitor, the voltage between its plates will rise according to Q is equal to CV, where Q is the charge stored on the capacitor, C is its capacitance, and V is the voltage difference between its plates. This is important because the insulating dielectric between the plates of the capacitor will break down if the voltage between the plates is too high. The simplest form of capacitor is a parallel plate capacitor, which consists of two rectangular metal plates separated by a dielectric, in this case, air. Now, the capacitance of the parallel plate capacitor depends on the area of the plates and their separation. And as I decrease the separation between the plates, you can see that the capacitance, as indicated on this meter, in picofarads, increases. And finally, I can change the area of the capacitor by changing how much the plates overlap. So watch what happens to the capacitance in picofarads as I decrease the area that the plates overlap. The equation that gives the capacitance of a parallel plate capacitor is C is equal to epsilon R, epsilon naught A over D, where epsilon R is the dielectric constant of a dielectric, epsilon naught is the permittivity of free space, A is the area of the plates, and D is their separation. We can also increase the capacitance of the capacitor by replacing air as a dielectric with something like plastic, cardboard, or even paper. And as we place the new dielectric between the plates, you can see that the capacitance increases. Provided the new dielectric completely fills the gap between the plates of the capacitor, the capacitance will rise by the dielectric constant of the new material. Capacitors can be used to store electrical energy. To work out the energy stored, you can use three versions of the same formula.
So here we have a really large capacitor. This is straight out of our national grid. It's 9 microfarads, and we're going to charge it up to 26,000 volts. Now, according to E equals half CV squared, that gives us 3,000 joules. And we're going to discharge all that energy through this tiny, thin copper wire. And we're going to do it using this high-tech switch. Three, two, one. All right, that was pretty cool. But now let's see what happens if we put the same amount of energy through an apple. 3, 2, 1. Woo. That apple got completely destroyed. All right, let's try a courgette. 1. So at the end of all of that, we got ourselves a fruit and veggie salad, all made with 3,000 joules.